Right, so we pick up things today, and the charger's had a pretty good clean and is cosmetically a lot nicer to work with. All of the fuses are now restored, and some of the screws have been tidied up where they've been a bit rusty. I've tried to clean those. All the knobs are now cleaned and polished, and most of the labels have been reconditioned. So now it's time to do some electrical safety tests before we actually go ahead and power up the unit. But for that we're just going to use a portable appliance tester, which will do the basic tests required, just to check that this thing is actually going to be safe to use. Now, because this charger is basically a big metal box, that's what's known as a Class 1 piece of equipment, and it requires an earth test. So for that we've got a big fat earth clip, and the tester is going to pass a hefty current down that cable and back up through the case of the body and the cable of the appliance itself. And hopefully that will show that there's a good sound earth on this piece of equipment. So I'm just taking the earth clip, and I'm just finding a decent piece of likely looking metalwork onto which to clip it, and then we'll run the test. So remembering to switch the units all to on, so we confirm that this is a Class 1 test. And it's now asking me where I want to set the fault current, and 0.5 ohm is typically okay for this piece of equipment, so we'll accept that. And now I've connected the appliance, connected my earth probe, and we can begin the test. Yes, I've given it a visual test already, so I don't need to do that again. And there we can see we have got a good earth, and we passed the test. Now for the insulation test, what that's going to do is it's going to join the line and neutral conductors together and put around about 500 volts on those, and measure if there's any leakage through to the earth conductor. So we'll go ahead and do that test now. And finally the tester will do a load test. It's basically just going to switch the unit on for a few seconds. Again, it's happy with those results. So that's a good sign that this unit is at least electrically safe, and it's not going to give me a nasty belt or anything like that just by its general operation. Obviously I'm not going to go sticking my hands inside it, as there's a lot of exposed live terminals. I think now we can proceed to a functional test. So we'll switch on the lighting battery charger first and test that. And we'll just explain the dummy load that we've got connected across the system at the moment. So that's an 8 ohm resistor, and we have a 12 volt car headlamp with both filaments connected in series. So arguably that's a 24 volt lamp now. And we can do a few basic measurements. First thing to observe is that we've actually got a correct full wave rectified waveform. So that's showing that all of the diodes are working in the bridge rectifier. Second thing to note is that we've got about a 30 volt peak to peak waveform there. That is of course into a resistive load, and it's not a battery. So that's why we've got the sinusoidal waveform there. Approximation to it anyway. And we can see that as we turn up the current control, the waveform slowly rises, and of course as the current goes up the waveform grows, and the bulb is glowing a bit brighter with each turn of the control. And now finally, if we connect up our 24 volt battery made up of two 12 volt batteries connected in series, we can see that we've got almost a DC voltage here now, as we would expect, with just little spikes. So finally, trying to make a little sense out of what the ammeter is actually telling us. The setup we've got now is the battery is a 12-volt battery connected to the vehicle battery charger. This is showing a current of around about half an amp, a little less than half an amp. But what exactly is that telling us? So what I've got set up now is the battery is being fed through an 8 ohm resistor, and the current flowing through that resistor is developing a voltage, and that is being monitored on the scope. So we can actually measure the voltage being developed across that resistor, and from that we can actually do some calculations and work out what the current is. And with the scope set to 2 volts per division, we've got a little over 3 divisions. Now, with the current control set to maximum, we still can't get an indication of more than an amp with this setup, but this is the only high power resistor that I've got easy to hand. Now you can see on the scope we've got a little over 6 divisions, and remember, these are the current spikes that are going into the battery. So if we now introduce a good old-fashioned AVO 8 into the equation, we can see that we've got a reading here of around about 350 milliamps. I hope you can see that. I can show that. And on the charger itself, well, very difficult to judge really, because you've got a very small scale deflection, but something under half an amp. If I turn the control up to its maximum now, we're still getting less than an amp here. Let's call it 3/4 an amp. And on the AVO, well, we're in the right ballpark, I would think, there, around about 650 milliamps. What we have to take into account, of course, is that the waveform is not a true sinusoid that's been rectified, because we've got bits missing from the waveform, because it's only the peaks that are going into the battery. So these meter readings are somewhat arbitrary, aren't they? And bear in mind that these sealed lead acid batteries are not really supposed to be charged with this waveform anyway. They're expecting a constant voltage charger. So maybe we need to think about putting some downstream modification to charge these batteries, and just use the charger as a glorified power supply. And to do that we would have to smooth the waveform with capacitors, and then probably feed it into a DC-DC converter to then charge the batteries indirectly. And that may well be the way forward with modern batteries.